Hi, and welcome to another adventure with Mr. Lamb. Today we'll just be discussing more about matrices. So in terms of the course outline, today we're doing binary, permutation, communication, and dominance matrices, the inverse matrix, and solving simultaneous equations using matrices. So first go guess is talking about binary, permutation, communication, and dominance matrices. So the binary matrix is a matrix that has only ones and zeros in it. For example, those two, the first 2 by 2 matrix has only 1 1 and the rest zeros. The second one is a row matrix with 2 1s and 1 0. Then we're moving on to permutation matrix. Now, permutation is a matrix where there is only 1 1 in each row and column, and the rest are all zeros. So as you can see here, a row permutation is when the permutation matrix is in front of the matrix or on the left of the matrix, as you can see here, so on the left hand side of this matrix. Now, in a row permutation, the row switches with the column depending on where the number 1 is. So in this example, the first one is in row 1, column 2, so row 1, column 2. So that means that row 2 will move to row 1. As you can see here, row 2, 258, has moved to row 1. The second one is in row 2, column 1, so row 2, column 1, this one here. So as you can see, row 2, 258, has moved to row 1, up here. And the last one, the third one, is in row 3, column 3, which means row 3 will move to row 3, or it just stays where it is. The column permutation is when the permutation matrix is on the right of the matrix. And notice it's in front. And this is also considered in front, depending on how you're looking at it. But we'll change the notes to column permutation is on the right, and a row permutation is on the left. So in a column permutation, the column switches with the row. So for example, the first one is in row 1, column 2. So row 1, column 2, which means column 1 will move to column 2. So column 1, 1, 2, 3, has moved to column 2. 1, 2, 3 here. The second one is in row 2, column 1, which means column 2 will move to column 1. So column 2, which was the 4, 5, 6, has moved to column 1. And the third one is in row 3, column 3, which means column 3 will move to column 3, which pretty much means it stays where it is. So just some hints and reminders and some special tips. A permutation matrix to the power of an even number becomes an identity matrix. If you've got something like this, and as you can see, there's only ones in the first 2 columns, then if you ever multiply this out, you only get numbers in the first 2 columns. The last one will be 0. If I'm looking at this one here, since the ones are in the first and the third column, then when you multiply this out, the numbers will be in the first and the third column, and the middle column will be zeros. Similar if you have rows, and if it's a row, it will be on the left of the matrix. The ones in row 1 and row 2, that means if you were to multiply this out, the first 2 rows will have numbers, and the last row will have all zeros. Communication matrix. Communication matrix is a square binary matrix in which the ones represent the links in a communication system, direct links. So a one-step communication link is the first matrix representation of the network. And it generally shows how many connections each person has, and normally represented by the letter C. So something like this. As you can see here, A can talk to B, A can talk to C. So as you can see, from A to B, there's one connection. From A to C, there's another connection. There's no connection from A to A, but there is no connection from A to D. Hence, there's a 0 there, and so forth. In terms of a 2-step communication link, it's represented by C squared, and it shows how many 2-step communication links there are. It's directly to D, but A can talk to C before getting to D. So as you can see here, to get the C squared or the 2-step communication link, all you have to do is square the C. The total number of 1- and 2-step links in a communication system is normally represented by T, and can be found by working out C plus C squared, like that. The next one is a dominance matrices. So a 1-step dominance matrix is similar to a 1-step communication link. However, dominance matrices are used to help identify who is most dominant, or which team is most dominant, or who is the winner. Dominance is worked out by summing the rows and is represented by D. So in terms of two-step dominance, is represented by D squared. Using D and D squared, we can determine the top ranked player, which is also represented by T. So to do that, the matrix is creating a dominance matrix is created by having the home team on the left and against team on the top, and the ones represent who beats who. So for example, A here and B on here. So A versus B has a 1, that means A beat B. Here A versus C has a 1, that means A beat C. This is the D squared matrix. To get the D squared matrix, you just need to square this matrix here. When you add the D and the D squared matrix, you'll get this matrix at the end, which we can also call T. The sum of the rows in this matrix tells us who is the winner. So as you can see, the first row, which belongs to Team A, has a sum of 4. Team B has a sum of 2. Team C has a sum of 1. And Team D has a sum of 0. Because Team A has the biggest sum, that means Team A is the winner in here. And then the next one is Team B, and the one after that is Team C, and Team D is last out of the 4 teams. So 2016 Federal Maths Exam 1, this was the question. You had to, using this method, Team C was ranked number 1, Team A would have been ranked 1 if the winner of one match had lost instead. So match was between which team. So in this one, you have to kind of trial and error and work it out. Here's a short video.
Okay, this is 2016 Federal Maths Exam 1, question 8. The matrix below shows the result of each match between 4 teams, A, B, C, and D, in a bowling tournament. Each team played each other team once, and there was no draws. In this tournament, each team was given a ranking that was determined by calculating the sum of its one-step and two-step dominances. The team with the highest sum was ranked 1, the team with the second highest sum was ranked number 2, and so on. Using this method, Team C was ranked number 1. Team A would have ranked number 1 if the winner of one match had lost instead. That match was between which one? So for this question, fortunately there's no real easy way of doing it. You have to go through it and check every single one. So first of all, I'll just bring up the matrix. So it's a 4 by 4. Okay, hit enter. Now I'm going to bring that matrix down. I'm going to square that as well. Now I'm going to bring that matrix down plus the squared, so then I don't have to redo it every single time. Now let's go for the first one. So the match between A and B, if that was reversed, so in terms of the matrix A and B, it will be, so that will still be 0, but this will be 1, 1, 0, and in this case it will be 0, 0, 0, 1. So that will be the change to the first 2 lines. The rest of it will not change at all. So this part here becomes a 1, this one here becomes a 0, and just change it in the other one as well, 1 and 0. Hit enter, so we're just testing out the answer to A. If we hit that, we get the matrix 0, 2, 1, 2, 1, 0, 0, 1, 1, 1, 1, 1, 0, 2, and 1, 1, 1, 0. Just a reminder, to check which one's the most dominant, you have to add the rows. So that's a 5, 2, 4, and 3. As you can see there. Now, because we've switched A and B, the results of A and B, Team A is the winner. So in this one, I guess we got lucky. The answer is A for that one. Otherwise, you have to go along and check each individual answer. And that's it. Thank you.
Alright, so that was 2016 Federal Maths Exam 1. Moving on. So 2016 Federal Maths Exam 2. Talking about sending direct messages. Here's a short video.
Hi, so this one is 2016 2016 Federal Maths Exam 2, question 2. The travel company has 5 employees, A, B, C, D, and E. The company allows each employee to send a direct message to another employee only as shown in the communication matrix G below. The matrix G squared is also shown below. The one in row E, column D of matrix G indicates that Elka, sender, can send a direct message to Dana, receiver. The 0 in row E, column C of matrix G indicates that Elka cannot send a direct message to Chen. To whom can Dana send a direct message? So let's look at this section here of the matrix. We've got Dana, so she's the sender, and then we've got the receivers on the vertical columns. So Dana can send a message to B, who is Ben, and Dana can send a message to E, which is Elka. Direct message anyway. Part B. Chen needs to send a message to Elka but cannot do this directly. Write down the names of the employees who can send a message from Chen directly to Elka. So let's look at who can receive messages from Elka. We have A and we've got D. So we've got sender A. So Mara can send it to Elka. And Dana can send it to Elka. But obviously Chen cannot send to Elka. So let's have a look at who Chen can send it to. Chen can send it to Amara, which can send it to Elka. Chen can send it to Ben, but Ben cannot send it to Elka. And Chen can send it to Dana, which can send it to Elka. So in terms of this question, Chen would need to send a message to Amara or Dana for it to be sent to Elka. And that's all. Thank you very much.
Alright, moving on. So 2017 Federal Maths Exam 1. This was question 2, another multiple choice.
Hello. So we're looking at 2017 Federal Maths Exam 1, question 2. The matrix below shows how 5 people, A, B, C, D, and E, can communicate with each other. A1 in the matrix shows that the person named in that row can send a message directly to the person named in that column. So for example, the one in row 3 in column 4 shows that Charlie can send a message directly to Jude. Esther wants to send a message to Bevan. Which one of the following shows the order of people through the message is sent? Alright, so we're looking at sender and the receiver. I'm going to start with Esther. So if we look across, Esther can send, so you look across and go to the first one. Esther can send it to C, Charlie. So A is right. And then that means Charlie will be able to send it to D or to E. So look at these. It can't be B and C because only Charlie can send to Jude or Esther. But obviously we can want to send it backwards. So Charlie can send it to Jude, which would be D or E. Who's a Jude? Send it to Jude and send to Alan or C, which is Charlie. So that's not backwards, so it's not D, it must be E. So we check it, Esther sends it to Charlie, Charlie can send it to Jude, Jude can send it to Alan, and Alan can send it to Bevan. And that's how we do that one. Thank you very much.
Okay, moving on. So 2017 Federal Maths Exam 1. So in this one, a permutation matrix P can be used to change fears into safer. Now, if we look at this, a permutation matrix needs to have only one 1 in each row and each column. And if you have a look at all the answers, you can eliminate 2 of them straight away. And that will be A and D. As you can see, there's 2 1s in this column, and there's 2 1s in this column. The next thing is just a reminder, row permutation, as you see here, if the 1 is in row 1, column 2, then row 2 will move to row 1. Let's have a look at the first letter, which is an F. The F has moved to row 3. So that means row 1 has moved to row 3, which means the first one will be in 3, 1. So you're looking at row 3, column 1. There should be a 1 in row 3, column 1, which is this one here. So the answer must be C. So just to go through that again, have a look at this sentence very carefully. The first one is in row 1, column 2. So the 1 is in row 1, column 2, which means row 2 will move to row 1. So if we do this backwards, the F has moved from row 1 to row 3. So there's a 1 here and a 3 here. So that means when we switch it back to put the 1 will be in row 3, column 1, which is that answer there. That one's a bit difficult, but have a look. The row permutation instructions are there. 2017 Further Maths Exam 1.
Hi, so this question is 2017 Further Maths Exam 1, question 5. 4 teams, A, B, C, and D, are competed in a round-robin competition where each team play each of the other teams once. There are no draws. The results are shown in the matrix below. A 1 in the matrix shows that the team named in that row defeated the team named in that column. For example, the 1 in row 2 shows that team B defeated team A. In this matrix, the values of F, G, and H are. So the first one is here, which is F. So this is A against C. Now, if we look here, C and A, C was the winner, A was the loser. That means when I go across, this one should be a 0 because A lost to C. So it cannot be C, D, or E. Now, having a look at this, let's look. We've got F's that are the same. We've got G's that are the same. Let's look at the H's. So the H's is D versus D. Now, D versus D, you can't play yourself in this game. So as you can also see, A versus A is 0, B versus B is 0, C versus C is 0. It means D versus D must also be 0. So that means B cannot be the right answer, and the correct answer must be A. So that's how you do that one. Thank you very much.
Okay, moving on. Alright, the second skill I guess we're looking at is the inverse matrix. So the inverse matrix, A to the power of -1 is what we call the inverse matrix. And A is the inverse, or A to the power of -1 is the inverse of matrix A. So if the matrix A is multiplied by the inverse of A, the resultant matrix is the identity matrix. It's like the opposite. So for example here, A times inverse of A equals to I, which is the identity matrix. Inverse of A times A is also the identity matrix, just switched around. Now likewise, if matrix A is multiplied by the identity matrix, the resultant matrix is also A. So A times I is also A, I times A is also A. Now the inverse matrix can be used to help you solve for unknown matrices. So example 1, if you've got matrix A, B equals to C, and you need to find the matrix B. So if the matrix A on the left must be removed. This is done by applying the inverse of A to both sides. So A times B equals to C. Now since matrix A is in front of matrix B, then the inverse of A must also be applied to the front of the existing matrix on both sides. So as you can see here, A to the power -1, or inverse of A, is applied to the left of matrix A. So when we do it on the other side, just make sure that it's also in front of that matrix, or on the left. The inverse of matrix A multiplied by A will become the identity matrix. So it becomes IB equals to inverse of A times C. Now therefore B is equal to inverse of A times C, because I, or the identity matrix, times the matrix B is just matrix B. Hence there. The determinant of a matrix. So if you've got a matrix A and the numbers are A, B, C, and D, then the determinant DET, so you can actually type that on your CADs, DET bracket and then the matrix. The determinant is A times D minus B times C. So it's A times D minus B times C, the two crosses there. If the determinant is 0, then there is no inverse matrix, known as a singular matrix, and there's also no unique solution. If the determinant does not equal 0, then there is a unique solution. In order to calculate the inverse matrix by hand, you need to follow the formula represented here. So if matrix A is A, B, C, D, then the inverse of matrix A will be 1 on AD minus BC, and then the matrix. So this was a 2 by 2, so the resultant is still a 2 by 2. The AD switch, as you can see, and the BC get an extra negative value, or a negative sign to it. So if b was originally -3, you attach another negative to it, so it will make it +3. Here's an example that you can have a look at. (2017) Federal Maths Exam 1. Which of the following matrices has a unique solution? So hopefully you remember a unique solution has a determinant of not 0. So yes, we'll go through each single one of them. So you go to your calculator, you can type DET, open up some brackets, and then you bring up your matrix, and then we'll go through one by one. So 1, 1, 1. So as you can see, the determinant equals to 0, so that one hasn't got a unique solution. I'll copy and paste. Let's try the next one, which is 8, -4, 4, and then 2. Hit enter. As you can see, that one gives me a number greater than 0 or less than 0, so it's not 0. That means the answer will be C, because it has a unique solution. First skill, solving simultaneous equations using matrices. So example 1, if I've got 2x minus 2y equals to 3 and x plus y equals to -1, you need to convert them to matrices first. So the numbers in here go in A matrix. We'll call that matrix A. So you got the 2 that goes here. We've got the -2. Don't forget the negative sign. -2 goes to the next one. You've got a number 1 here. If there's no number in front of a letter, then it's the number 1. So number 1. Don't mix that up with having no letter. If there's no letter there, then that's the 0. And then you put the two variables that you're trying to find, which is x and y, in a matrix called X. And then you put the answers in a matrix called C, and they're at the end. So then you make the formula A times x equals to C. You multiply both sides by inverse of A to get x by itself. So as you can see there. So we apply the inverse of A on the left-hand side of the matrix A, and then we apply the inverse of A to the left-hand side of matrix C. The inverse of A multiplied by A just becomes our density matrix, and therefore matrix X, or the unknown, is equal to the inverse of A times C. And you can do that on your CAS calculator. So you do A to the power of -1 multiplied by C, and that will give you the inverse of, well, will give you the solution to x and y. So unique solution, once again, happens when the determinant of a matrix is greater than 0. If the equations are graphed, then there should be an intersection point. They should cross over. There will also be an answer when a set of simultaneous equations is solved. An inconsistent equation is when the determinant does equal to 0. If the equations are graphed, there should be no intersection point, which means there's no solutions. And they should be parallel lines that never intersect. A dependent equation happens when the determinant also equals to 0. If the equations are graphed, there should only be one line, so no unique solution. And they are both the same line. If you want to graphing this on the CAS, you go to Add Graphs, menu, Graph Entry, Edit, and click Relations, and type in both equations exactly as they are. So for inconsistent equations, there should be two lines parallel to each other, and they'll never intersect. Whereas the dependent equation, it should be one line, one on top of another, like shown. And that's it. So this is our second lesson summary. Today we went through binary, permutation, communication, and doubleness matrices. We went through the inverse matrix, and we went through solving simultaneous equations using matrices. Thank you very much.